Welcome all, and good evening. I'm Anya Hurlbert, Professor of Visual Neuroscience at Newcastle University, and it is an absolute delight to be hosting tonight's lecture by Professor Jim Al-Khalili on the joy of science. This lecture is presented in association with Blackwells to mark British Science Week, and you can buy signed copies of Jim's new book, The Joy of Science, from Blackwells online. Look at the link below. Just a note on proceedings, Professor Al-Khalili will be answering questions live after his lecture. So please, if you would like to ask Jim a question, send it in writing to the YouTube live chat box on your screen or via Twitter at InsightsNCL. And if you're tweeting about the event and want to share your thoughts, please use hashtag InsightsNCL. And now to tonight's main event. It's a huge pleasure to introduce Professor Jim Al-Khalili, world-leading quantum physicist and multiple award-winning science communicator. He holds 2 professorships at the University of Surrey, a distinguished chair in physics, and a professorship of public engagement in science. And somehow he must be tunneling through time to do so many things at once, writing and broadcasting around the world, while making fundamental contributions to theoretical physics, particularly in nuclear reaction theory, and most recently, quantum biology. As a scientist, author, and broadcaster, Jim gets to the core of the very stuff we're made from. He's probed the nuclei of atoms and discovered quantum effects in DNA. As the host of the long-running weekly BBC radio program, The Life Scientific, he's also revealed the inner worlds of scientists themselves. Jim is also past president of the British Science Association and a recipient of the Royal Society Michael Faraday Medal and the Wilkins-Bernal-Medawar Medal, the Institute of Physics Kelvin Medal, and the Stephen Hawking Medal for Science Communication. He received an OBE in 2007 and a CBE in 2021 for services to science. He's a regular presenter of TV science documentaries, such as the Bafta-nominated Chemistry of Volatile History. He's written 14 books on popular science and the history of science, and he's here tonight to talk on the topic of his latest book, The Joy of Science. Let's welcome Professor Jim Al-Khalili.
Good evening, everyone, and thank you, Anya, for that lovely and rather cringe-worthy introduction. It's a pleasure to be here. I was just saying to Anya earlier that while it's nice to attend and give talks face-to-face, sometimes doing them remotely has an advantage, and that really does apply in this case because I tested positive for COVID yesterday. So I am in any case isolating here in my study at home down on the South Coast. I wouldn't have been able to come up anyway. So just as well, this is a remote lecture. As Anya mentioned in the introduction, I want to say something about this new book, which comes out next month, but apparently Blackwell's bookshop are already selling it. So I'm very excited. It was published by Princeton University Press. So I'd finished writing it about a year ago. And of course, the process of publishing takes a while, particularly in the US. So it's only now that it's, I can share it with the world. Unlike my other books on popular science or on the history of science, really this is more about celebrating what's good about how we do science, the scientific method, and hopefully not coming across as sort of patronizing. I suggest to the readers that wider society could probably benefit a little from our sort of daily interactions, making use of the scientific method, the way scientists carry out their work. First of all, to say that science, unlike, I think a lot of people think that science is somehow a collection of facts about the world. That's science. No, that's not science. That's knowledge. Science is a process, or a way of thinking, certainly, that enables us to get to that knowledge, get to those facts, to make sense of the world. Of course, there are many ways of gaining insights and knowledge about our world, whether it's through meditation, whether it's through reading text, whether it's through art and literature and poetry, whether it's through contemplation and debating and discussing with people. But if we want to find out how the world really is, the true nature of what I call physical reality, the true nature of reality, objective reality, then science has a great advantage, because science relies on the scientific method. And so I want to say something about what science is. What is the scientific method? What distinguishes science from other ways of thinking, of gaining knowledge, gaining enlightenment? In science, you can imagine a scientist, a cosmologist, or an astronomer gazing up at the heavens and making observations of the stars, figuring out the nature of the universe. But you can also imagine a medic carrying out clinical trials, or a chemist working in a lab, mixing chemicals and studying the nature of the way matter interacts with different kinds of matter and materials interact. Or you can think of, I'm trying to, here we go. Oh God, no. I was clicking and the clicking was taking me too far. Anyway, I'm back. Or we can think of climate modelers developing computer codes to study the Earth's climate. Or of course, Einstein scribbling algebraic equations on a blackboard. All of these are very different ways of learning about our world, but they all share this process, the scientific method. So I've certainly, as Anya mentioned in the introduction, for over 10 years now, I've presented the Life Scientific on Radio 4. In fact, Anya was one of my guests a while back. And that's given me an insight into just how broad science is, the different kinds of ways in which we approach, develop an understanding of the world. And I think the Life Scientific has been important in that sense, because it gets across to wider society as well. Not only fascinating guests and fascinating life stories and wonderful scientific discoveries that have changed our world in some way, but also it gives people an insight into how scientists think, how they carry out their work. And in that sense, science is rather different from other ways of thinking. So what is it that distinguishes science from other ways of thinking? Well, you could say to be a scientist, one has to be curious, or that one has to come up with a hypothesis and test it in some way, look for evidence to support that or refute that hypothesis. But then, historians come up with hypotheses. Historians look for evidence and data to support that hypothesis, the narrative. Is then history a part of science? No, but history and science both have this in common: the testing of ideas, testing of hypotheses against data, against evidence. What about the idea of curiosity? Well, being curious about the world isn't enough. A conspiracy theorist would argue that they are being curious, that they are looking for evidence to support their idea, that they are thinking rationally. So is a conspiracy theory a form of scientific theory? There's a big distinction here. Ask yourself what it would take, what evidence it would take to persuade a conspiracy theorist that their theory is wrong. And I think you'll find they'd have to admit that nothing would. By its very nature, a conspiracy theory is irrefutable, whereas a scientific theory has to be refutable. We have to be able to test it, and if it's wrong, change our minds. Either improve it or throw it away or whatever, but we have to be able to test our theory in a way that conspiracy theorists don't. Another property or aspect of the scientific method is that our hypothesis or our scientific theory has to make predictions that we can test against. Well, your star chart makes predictions. So is astrology a form of science as well? I mean, we've all heard, the people who confuse astrology and astronomy, and scientists get very annoyed by that. But imagine you read your star charts one morning, and it says, today you're going to receive some good news at work, and for whatever reason, your boss gives you a promotion. There you go. The prediction of the star chart came true. Does that make it science? No, it was coincidence. Okay, we know that astrology isn't part of science, that it's based in superstition, and it has no basis, that there's no way we can explain it using the laws of physics as we understand them. Well, very often people take their trust in science too far and assume that anything that sounds vaguely scientific must be true, must be correct. And we often hear, people talking about various alternative therapies, for example, pseudoscience, but because the wider public, through no fault of their own, find it difficult to discriminate between good science and bad science, they tend to be more trusting than they should be. And of course, we've seen that very clearly in the last 2 years during the pandemic, where it's very difficult for wider society to be able to separate out the good science, the evidence that is based on a careful collection of data by experts, and the science that's based on mere opinion of people who just simply want to support or argue for a particular ideological view. One of the things about what's happened during this last 2 years, during the pandemic, is that scientists have been in the spotlight. And the scientific method itself has been in the spotlight. So it's more than, for someone like me who communicates science, first and foremost, I want to instill, excitement. I want to inspire, talking about exciting science that can get people excited by, new discoveries about the universe, for example. But there's another aspect to it. Another reason why communicating science is so important is because we can get across how science works, getting across the scientific method. Because now more than ever, wider society needs to know who to trust, where we are bombarded with information all the time. A lot of it is very easily accessible. How can people work out who to trust, what to believe when they see something online, for example? And partly that's the reason for my writing this book, to give people an idea of, borrowing what's best from the scientific method. Now, of course, scientists are not fallible. Scientists are not perfect. They're fallible. They make mistakes. They have their own biases. They have their own ideological drives. They're not all honest. But the great thing about the scientific method is that corrects for this. So here are then 8 lessons, very, very quickly. I'm going to work through them quickly because I don't want to take too long. I want to give you all enough time to ask me questions. 8 lessons borrowed from how we do science that I think would serve us well in our everyday lives. So lesson 1 is about the nature of truth. We seem to live increasingly in a society where truth is what you want it to be. It becomes subjective, relative. There are very good and important things about what's called cultural relativism. Simply respecting other viewpoints, other cultures, other opinions. But when truth also gets mixed up, and becomes something that we as a society, as a culture decide on, we build it from nothing, then we're in deeper trouble. In particular, when it comes to truths about the nature of our world, something is either right or not. You know, you can't make up your own truth to suit you. So I'm going to give you several statements, several facts that are either true or not true. And I would argue they are incontestable. Humans have walked on the moon. True. The Earth is flat. Not true. Life on Earth evolved through a process of natural selection. True. The world was created 6,000 years ago. Not true. Earth's climate is changing, mainly due to humans' action. True. Nothing travels faster than through space than the speed of light in a vacuum. True. Give or take, there are roughly 7 billion atoms in the human body. True. 5G masks contribute to the spread of viruses. Not true. Now, there may be people out there listening to this talk who might wish to contest one or other of these points. And by all means, you know, please bring them up in the Q&A later. But I would argue that were any of these the opposite of what I have stated here, that would require the whole edifice of modern science to be dismantled and rebuilt. Because these are not simply opinions. These are not simply based on ideological motives. These are facts about our world that are either true or not true. And if you have an alternative explanation, that alternative explanation needs to explain everything if it's going to dismantle, if we're going to dismantle the laws of physics and chemistry and biology, because they predict these statements, then you have to come up with something, an alternative that will explain everything else that those theories explain so successfully. When it comes to the affairs of, you know, people in culture, in society, when we're talking about moral truths, then of course the situation gets much more hazy, much more muddy, and it's not straightforward to say something is true or not true. Then, you know, very often it becomes context dependent. Well, it might be true in this situation, but not in that. You know, human behavior and human affairs, as any psychologist or sociologist will tell you, is far too complex to be sort of broken down and distilled into a few equations like I work with in physics. But nevertheless, given the context, something is either true or not true. Okay? And you can't make up your own truth. You can't create your own reality, as was done by some politicians in America, for example, quite recently. You know, that's called solipsism, creating your own reality. There's a physical reality out there in which stuff happens that are either right, true or not true. Lesson 2 is more complicated than that. Very often we hear what's called Occam's razor, which says that the simplest explanation is often the correct one. But that's not always the case in everyday life. Sometimes things are a little bit more complicated, and we have to accept that. There's been a real drive, particularly with the advent of social media on the internet, for distilling issues and topics down to the lowest common denominator, to lose all nuance. You hear this a lot now. Everything's black or white. Arguments on social media, you're either with me or against me. No one's allowed to say, well, you know, you've got a point, but you've also got a point, and the truth is somewhere in the middle. It's fuzzy, it's hazy. No, it has to be. I mean, it sounds like I'm arguing against my previous point, which is something's either true or not. But when it comes to human affairs, sometimes you have to dig deeper to get to that truth. Unfortunately, many people aren't prepared to put in the effort. We wouldn't get very far in science if we just thought, well, this hypothesis seems right, it sort of makes sense. It's the simplest explanation. That's the way the world is. We wouldn't get very far in science if we had that attitude, because sometimes the simplest answer isn't always the correct answer. You have to work a little harder. And particularly in everyday life, real life is messy. You know, as a science communicator, I try and distill complicated scientific issues into something simple. But I try not to lose the essence of what I'm talking about. I will get rid of all the subtleties and details that are not necessary. But if you throw out babies with bathwater, sometimes you can just go in the completely the wrong direction. Okay, lesson 3, mysteries should be embraced, but we should also try to solve them. I included this because I think for a lot of people, there's this perception that science is about cold, hard rationalism of removing all mystery and magic from life. Everything's, you know, neatly packaged and understood. And nothing could be further from the truth in science. Science is all about embracing mysteries. If there weren't mysteries out there to be solved, we wouldn't have a job to do. It's linked to this idea that somehow science isn't creative, which of course, again, we know is not true. It's just as creative as anything in the arts. Richard Feynman, the great American physicist, said, poets say science takes away from the beauty of stars, mere globs of gas atoms. Nothing is mere. I too see the stars on a desert night and feel them, but do I see less or more? What is the pattern or the meaning or the why? It doesn't do harm to the mystery to know a little bit more about it. Learning about our world, digging in a little deeper, finding out what the mystery is, finding out that something is slightly more complicated than we thought, can be empowering, can be enriching. And it doesn't have to, everything doesn't have to be simplified down to a tweet or a meme. I wanted to say something briefly while I'm on this lesson about the famous allegory of the cave. It goes back to the Greek philosopher Plato, which highlights the importance of wanting to understand, wanting to solve mysteries about our world. The story very simply goes like this. Imagine you have these prisoners who are, I mean, I know it's very mean, but look, it's just a story. Prisoners chained inside a cave. They are unable to move and look around and see what there is behind them. So all they can see are shadows on the cave wall in front of them that are created by objects carried by people walking behind the wall. The prisoners hear voices and sounds of people talking, and they think those voices come from the shadows themselves, echoing around the cave. For the prisoners, those shadows, those two-dimensional shadows, are reality. That's their entire world. They know no different. Imagine one day one of the prisoners is released and he is allowed out of the cave and up above ground, where he sees true reality. He sees a three-dimensional world. He understands that shadows are simply where the light from the sun or some other light is blocked because it can't pass through a solid object. So he understands the nature of shadows, and for him, the world is much richer. Imagine if he were then to go back into the cave and tell his fellow prisoners about this new, richer reality. Well, they think he was crazy, wouldn't they? After all, they know no different. Although this is thousands of years old, this allegory, it's certainly been tackled by Hollywood movies. Think of the film The Matrix or The Truman Show, where there is an external real world, and the world that we think is real isn't. It's even led to certain philosophers talking about whether our reality that we perceive is also the the full reality, whether there's an external reality, excuse me, and you're going to have a slight coughing fit at some point during this talk. Here we go. So, maybe we're living in a simulation. Maybe there are higher beings that have created, the matrix, and we're living in that simulation. I don't buy that. I don't think it holds water. I think if you say that, then you have to also argue, why is it that the beings that created the simulation that we live in aren't themselves also simulations? And the beings that created their simulation, why aren't they? And so on, ad absurdum. So I don't think that holds. Well, yeah, I really thought my voice was going to hold out very well, but we'll see. Lesson 4, just because you don't understand something doesn't mean you can't if you try. We know, we hear there's the famous, we don't need experts quote from a few years ago. But if we take something like quantum mechanics, nobody expects, I don't expect everyone to be an expert on quantum mechanics in order to trust someone who does understand quantum mechanics to say that, this is the way the world is down at the subatomic scale. No different to, if I don't claim to be an expert on plumbing. I trust my plumber to fix my boiler. I'm not an expert. I'm not a concert pianist. I couldn't run the 100 meters. Oh, there we go. Everyone, people devote their lives to developing different skills, or they're maybe born, have some natural ability, but the fact is, we are bombarded with information all the time now, and we have shrinking attention spans. The problem is that very often we are not prepared to trust someone who has put in the effort to understand a subject. But, you don't need a PhD in climate change to appreciate that recycling your rubbish is a good idea. Similarly, I don't say to my plumber, don't worry, you don't need to fix my boiler. I've had a look on YouTube and I can see what's wrong with it and I can fix it myself. These are things that would, areas of expertise that might take years to become an expert in, but it doesn't do any harm to learn a little bit about a subject if we put in the effort. Which takes me very naturally onto lesson 5. Don't value opinion over evidence. How often have we heard it said, or maybe we've experienced it in particular on social media, that someone's opinion somehow they claim is more valid than evidence, than data. But it is difficult for many people to know who to trust, to discriminate between evidence and mere opinion. Particularly, for example, during the pandemic, it's been difficult to know, whether it's to do with wearing masks and social distancing, whether it's to do with the vaccines. People don't deliberately want to learn something that is wrong, but we have to be able to filter and sift through all the information that we're receiving. So applying a scientific approach to assessing whether a particular bit of information is true or not can be very, very useful. It can help us separate between truths and untruths. It also, what we do in science is that we ask ourselves whether what we are reading or hearing about is true or not, and why do we believe it? And so, we have to examine our biases, whether we're hearing something, whether we believe it because we want to believe it. Are we examining our motives for believing something is right or wrong? And we see this a lot in everyday life today. I mean, we're talking in the news about people in Russia who only have access to state news, getting a very different and wrong picture of reality because they are unable to. They're not given access to other points of view to know what is true and what isn't. And one of the ways of tackling that in science, we like to think we do very well. We don't always do it very well. We like to think that the scientific method helps us here, is to recognize our own biases before we judge the views of others. So when you're arguing with someone, whether it's, they make some conspiracy theory claim, or it's, it might even just be usual, the sort of ideological difference of opinions, political opinions, or opinions about art or sport or music. Sometimes the view that you hold really is subjective. I may like a certain kind of music and you may like a different kind of music. None of us is going to argue and persuade the other one that they're wrong. But there are views and opinions about how the world is that are wrong. And it may not be, however strongly you hold your view, it may not be you who are right. So before you argue against somebody else's view that you disagree with, examine your own biases, examine where you received your evidence from, and whether that was something to be trusted or not. One of the problems we have in society, which I think social psychologists know very well, is something called illusory superiority, where a person has an overinflated sense of their own opinion and competence, but at the same time, not being able to recognize their weaknesses. We see this on social media. The people who shout the loudest tend not to be the people who understand a topic deeply enough. In fact, the experts on a particular area also know where there are gaps in their knowledge. So they tend to stand back. They tend not to be so strident and confident in their views. And what that does is just leave the debate to the no man's land is bare, and you just have the trenches of the two opposing sides shouting loudly, but not necessarily, these are not necessarily the people who know enough deeply about that particular subject. Don't be afraid to change your mind. So this is, in a sense, the most important feature of the scientific method, of how our scientists behave. Wouldn't it be refreshing if politicians could admit their mistakes? You see, in science, one of the most important features of science is uncertainty. Never being 100% sure that you're right, always leaving room for doubt. So when new data or new evidence comes along that might go against what you currently think, you have to be prepared to change your mind. In science, changing your mind, admitting that you were wrong about something, is a strength. It's a good thing. In politics, it's perceived as a weakness. Wouldn't it be refreshing if people could admit when they were wrong? Because in science, that's how we learn. That's how we develop. If scientists never admitted they were wrong, if they stuck doggedly to whatever hypothesis or theory they had, then we wouldn't have made advances. Okay, we would still be using the same old theories that we developed right from the beginning. Doubt, says Voltaire, is not a pleasant condition, but certainty is absurd. This takes me then to my final lesson, stand up for reality. We don't create our own reality, okay? That's called solipsism. As I mentioned earlier, think of the Donald Trump campaign denying the election results. You can't make up your own reality because it suits you. But how do we counter this? How do we make sure we live in a world where we can rule out fake news? I think as a society, we need to change, to adapt, better civics, better critical thinking, developing a more rational worldview. But we're going to have to make use of technologies. At the moment, for example, with AIs, at the moment, it seems a bit scary when you go onto Amazon or Netflix and you're presented with a product or a movie that you might like, because it knows, the AI knows, the algorithm understands your preferences, and it wants to show you something else similar to what you may have purchased before, or a movie that you watched before. So we sort of see that as slightly insidious. But we are going to have to use technology to help us filter out all the information, from the misinformation, from the disinformation, from the fake news. It becomes problematic, of course, because who decides then what is the fake and what is the true? Soviet propaganda, the Russian, although they want to go back to Soviet times, the Russian propaganda machine now is talking about, we see that they're saying, that's fake news, this is true news. So, who controls the technology that does all the filtering? I think society on the whole is doing very well in terms of, we're learning how to make use of technology. We're starting to develop ways of discriminating between the information that's coming to us that is based on good data or bad data. We still suffer from certain conditions that have been around forever. Confirmation bias, the fact that you only hear views and opinions that you already agree with, and we've always had that. In the past, we'd only read one particular newspaper that we knew had the political views that we shared, and so we didn't bother reading a different kind of newspaper. Now that we have the internet, now we have access to so much information, we still tend to gravitate towards those views and opinions we already agree with, and we can't do that in science. I mean, I know scientists do. Scientists suffer from confirmation bias the same as everyone else, but the scientific method ultimately corrects for that. Bad ideas never last too long in science. A related problem is what's called cognitive dissonance, where you genuinely get a sense of discomfort when you're faced with evidence that goes counter to what you already believe. You'll either dismiss it as fake news, or maybe sometimes you'll even use it and twist it so that it helps support your pre-existing views. So these are problems that are not going to go away. But on the whole, I am an optimist about the world. And in these dark times, sometimes it can be difficult. But here's why we should celebrate science. 4 points for why science and the scientific method is a good thing. First of all, science as a process is a reliable way to learn about how the world is. It has replaced superstition and ignorance. Enlightenment is always better than ignorance. It's always better to climb out of Plato's cave. Secondly, of course, science works. Without it, I wouldn't be talking to you now. We can't all shun science because of how it might have been put to evil uses, and therefore we assume all of science is bad. Science is empowering. It can benefit us in our everyday lives, which is what I try and get across in this book. But science also enriches us. It gives us a view of the world that is not only empowering, but is inspiring, is joyful. Science is not cold, hard facts that some people believe. Science is about embracing our ability to be able to make sense of the world. And that is always a good thing. So I will end there. I don't know if I have done for time, but I will, I guess, stop screen sharing and happy to take questions.
Thank you very much, Jim, for that inspirational call to action. We should all be thinking more scientifically in our lives and learn from you who have demonstrated that not all scientists, and particularly you, the scientist, are cold, hard, and unfeeling. You clearly care about people and the way the world is going. I think it's a very persuasive argument you've laid out. And clearly, our audience thinks so too. We've already got questions pouring into the chat. So we're now in the live Q&A session. And what I'd like to do is just read to you, because I can see the questions. I'm not sure you can, some of the questions that have come in. So first question is from Jamie. What are you excited about now in the field of physics and more broadly in science?
Well, thank you, Jamie. At the moment, for me, in my research area, I'm mostly interested. I mean, I'm a quantum physicist, so I study the world of the very small, and some of the exciting technologies in quantum mechanics are really sort of starting to ramp up and build up ahead of steam. Things like developing quantum computers and so on. I'm a theoretical physicist, so I'm interested in studying the nature of the quantum world using equations. And one of the fascinating areas for me is how we reconcile quantum mechanics with our everyday world. You know, in the quantum world, down at the level of atoms, things behave very, very differently. And for a century now, we've known this, and we've used quantum mechanics and we've developed technologies, but we're still unclear about how quantum mechanics and our everyday world sort of mesh together. And so we're developing models and techniques that are sort of taking us towards that area, which I find very, very exciting. I've got some PhD students and postdocs working on various theoretical calculations. And in a sense, because I the last 20 years, I've been very active as a science communicator. For the last 2 or 3 years, I've sort of gone back in and immersed myself more in my research. And I've always said that, if push comes to shove, I'll never give up the day job. I'm first and foremost a research scientist, and I want to carry on doing that research. In science in general, of course, there are all sorts of exciting areas and I get to hear about those, the exciting topics in science, by interviewing my guests on the Life Scientific. And there are so many, the world is so full of, so buzzing with all these different ideas and exciting discoveries and questions that we still have to ask, that I think it would be unfair to try and pick one out from among them.
Fantastic, thank you. We have a question from Nicole. As more is learned about dark matter and its role in quantum physics, I wonder if we could benefit from reframing how we think about it. If you had the chance to rename dark matter, what might you call it instead, knowing what you do now?
Yes, I mean, the term dark matter probably isn't very appropriate. I think it's much more appropriate to have called it invisible matter or transparent matter. We know it's out there. We know it has a gravitational influence. It holds galaxies together. It might have even, we think now it was important in developing the early structure of the whole universe itself after the Big Bang. But we don't know what it's made of. We think it's made of some new kind of particle. We don't know what kind of particle that is. But yeah, invisible matter or transparent matter would be much better than dark matter.
Thank you. Time to rehabilitate dark matter. From Annette, what brought you to this field of work? Were you an inquisitive child?
I think all children are inquisitive, aren't they? The difference, I'd always say, the difference between people like me and Anya who become scientists and pursue our career is about scientific research and discovery, is that we have never stopped being curious. For a lot of people, you're curious as a child, you ask your parents, why this, why this, why this? But at some point you grow up and, you're faced with all the other realities of everyday life and you stop asking questions. So I don't think I was any more inquisitive. Certainly by the age of 13 or 14, I realized I fell in love with physics as a subject. For me, that was the subject that I felt I needed to learn more about if I wanted to find answers to questions like, does space go on forever? What does the inside of an atom look like? What happens if I jump into a black hole? All those, the exciting, sexy questions in fundamental physics. I realized I had to study the subject if I wanted answers. And basically, I've never looked back since then. I'm still asking those questions.
So this is a question from Sally. As an academic, how do you balance your research with your time spent on science communication? I did notice that your website says your office hours vary.
Yes, they absolutely. I mean, it really is. It depends. Broadly, I think certainly over the last 15, maybe 20 years, I would say it's roughly a half and half split. So half of my time, I'm an academic. I still teach undergraduates. I have my research program, PhD students. I do sort of the various duties that you have to do at university, but condense into half the time. And the other half of the time, I'm a public scientist. So I do the radio broadcasting, the writing, TV documentaries. But it's not, I can't split it up and say in a week, today is my research day. Tomorrow I'm working on filming a new TV documentary. There'll be whole weeks of time when I'll be away filming. There'll be times when I'm not doing any public engagement and I'm sort of immersed in, I don't know, marking exam scripts or writing a research proposal. It's a difficult balance. And I think it was something that when I first started in science communication wasn't the accepted thing to do. You were deemed, if you were going to become a science communicator, then somehow you had given up on serious science. You'd become a media tart. Nowadays, I think it's certainly universities, certainly in the UK, more so than I think any other country, it's acknowledged that communicating science is important. Science communication is a perfectly good career. But when people ask me, how to get into it, I will say, first you have to decide, do you want to be a science communicator, perfectly good career, or do you want to be a scientist who communicates? And it's the latter the path that I have chosen. I want to carry on doing the science at the same time as communicating it. I just have to balance my time very, very carefully and learn to say no, that sort of thing.
Well, it's certainly true. I think practicing scientists know this, that there's much more emphasis put on what we now call public engagement or patient and public involvement and engagement. And that's all about communicating what one does, and indeed involving non-scientists as much as possible in the science. So I do want to move to another question that's come from Claire. How far can we push research facilities like CERN to find answers? Will some things always be theoretical to us tiny humans on an insignificant planet?
I mentioned at the end of my talk that I'm an optimist. I think it's incredible how far we've come. And there have been time and time again throughout the history, certainly of modern science, occasions when we felt, well, this is as far as we can go. Beyond this is metaphysics. Or if you have a religious faith, beyond this is the divine creator, and we can't really find a scientific explanation for why this is the way it is. But time and time again, science has pushed those boundaries back. We used to say, well, there was nothing before the Big Bang. You can't even ask that question because time didn't exist before the Big Bang. That's when time itself was created, according to Einstein's theory of relativity. Now you have cosmologists talking about there was something before the Big Bang. In fact, our Big Bang may not have been unique. There may be other universes with their own Big Bangs taking place in what's called the multiverse. Certainly in terms of zooming down, looking for the building blocks of matter and what we can do with a Large Hadron Collider. Yes, it's been slightly disappointing and frustrating that the Large Hadron Collider hasn't discovered anything apart from the Higgs boson, of course, which is very important. But that particle was predicted by Peter Higgs and others. So in a sense, it wasn't a surprise. It would have been more surprising if we hadn't found it. But it's surprising that we haven't found other particles. For example, the particles of dark matter. I don't think we've come to the end of the road. Whether nations have the will or the financial ability to club together to build an even bigger, more expensive accelerator remains to be seen. But there are other we're not twiddling our thumbs. There are plenty of ways. Certainly, I'm talking here about, obviously, about fundamental physics. There are many clever experiments being developed to probe the nature of reality in ways that don't require building bigger and bigger machines. So there's lots more to come. I'm not giving up hope yet.
Thank goodness for that. Just before we move to the final question, I wanted to throw in a question of my own, if I may, because you've talked about biases. And to me, it feels that in theoretical physics, where the facts seem harder and surer than in biology and psychology, where I work, it would also seem the case that perhaps one's own biases would be less interfering. And I just wonder, in your own research, have you had to deal with any biases that you've had to overcome in developing theories or proving theories or
Yes, I think, absolutely. It happened probably on several occasions. You know, when you invest enough time and effort developing a mathematical model of something, for example, back when I was doing research in nuclear physics, and I was studying the nature of nuclear reactions and the structure of subatomic nuclei, how the protons and neutrons are arranged inside a nucleus, and you use standard models to calculate these properties, and you produce some results. And then you're faced with someone maybe doing a different calculation that makes a different prediction to yours. And of course, you will argue that yours is right, because you can see why you've done what you've done. But there have been occasions when you have to admit, when you look at an alternative rival scientific theory, that it is actually better, that it does something that you had forgotten. And you have to say, actually, I'm going to have to change my mind about this, because that my theory doesn't make as good a predictions as yours, and I'm going to have to change my mind about it. So yes, even in physics, where we like to think there's an objective reality out there, the world is the way it is, and it's all we're getting closer and closer to that truth. Every now and again we realize we've gone up the wrong pathway and have to admit that we've got lost and got to head back again.
That's very illuminating. Thank you. I do need to move on to the final question, which is from Ian, and he asks, "What do you hope that readers will take away from your book?"
Interesting. I mean, I thought originally when I was writing it that readers will learn the lesson. Oh, the way scientists view the world is so powerful and useful, and I can make use of some of those ideas, and maybe help me overcome my biases or empower me more to understand the world. But actually, I'd like to think that it's a celebration of science, that it inspires people. It's not I want the book to inspire rather than be some sort of a self-help book. If you know what I mean. That's not the aim. Celebrating why science is successful, and why that's a good thing, how it might help us in everyday life, fine. But ultimately, I mean, I start off in the book talking about the beauty of a rainbow, and other authors, Richard Dawkins, Carl Sagan, have written about, Richard Feynman, the beauty that we can discover in our world if we apply some of the ideas from science, that it enriches us. Well, I picked the example of the rainbow, that learning more about how a rainbow is formed actually makes it more wondrous, more beautiful. It doesn't make it cold and hard and sterile if we use science to look at the world.
Thank you for that. And I have to say, I've had a glimpse of the book already, and I totally agree with you. Your example of the rainbow is spot on, and excellent. One of the most beautiful economical explanations of how it works, and just demonstrates what a brilliant science communicator you are. And I think you have helped us celebrate science and inspired us all to think in a more rational way about everything in the world. So thank you very much for that, Jim. And I'm afraid that is all we have time for from Professor Jim Al-Khalili. And thank you very, very much for joining us tonight. And thank you to our audience also for watching. I do just need to put in a plug for our next event from the public lecture series at Newcastle University. That will be on Thursday, the 17th of March, Tyneside Geographical Society lecture, Pocketbooks, Cairns, and Carrier Pigeons, Polar Postal Systems by Nancy Campbell. And we do hope that you will join us next time. And thank you again all for joining us tonight. And thank you, Jim.
Thank you very much.